good. So glucose, it's simple sugar, and its formula is C6H12O6. So glucose plus fructose gives us sucrose, which is like table sugar. So we would call this a monosaccharide. It's a simple sugar. So that's the actual number of carbons, hydrogens, and oxygens in a molecule of glucose. So we would say this is the molecular formula. What would be the empirical formula for glucose?
H2O.
Couldn't hear you.
CH2O.
Yes, CH2O. Because for every one carbon, there's 2 hydrogens and 1 oxygen. So this would be the empirical formula.
Is that why sugars are called hydrocarbons?
So anything with carbon and hydrogen in it is called a hydrocarbon. Yeah, like generally a hydrocarbon doesn't have any oxygens in it. It's just carbon and hydrogen. So if we looked at the mass ratio of carbon and hydrogen and oxygen in glucose, we would get a ratio of 1 mole of carbon to 2 moles of hydrogen to 1 mole of oxygen. That would be the ratio, but that wouldn't be the actual formula. The actual formula is this, but you can see the ratio is the same. So when we get data like this, where we have a percent of the total is carbon and a percent of the total is other things, the only thing we can deduce is what is the empirical formula, because we don't know exactly how many carbons, hydrogens, and oxygens are there. We only can figure out the ratios of them. So what other information would we need? So if we get an empirical formula, what other information would we need to calculate the molecular formula?
Molar mass.
The mass of 1 mole, right? Because we would figure out that the mass of CH2O would be 12, 2, and 16. That would be 30 grams in a mole. But if we were able to measure the molar mass of a sample of glucose, we would see it's actually 180 grams per mole, or 6 times as much. So that's why we would take this empirical formula and multiply everything in it by 6 and give us C6H12O6. So let's see how we do an example like this. So when we say a compound has this percent of carbon, this percent of hydrogen, this percent of oxygen by mass, what does that mean? How are we going to express that in numbers we can use?
You can assume it's out of 100 grams.
Out of 100 grams, right?
Yeah.
Exactly, because basically what it's saying is that out of every 100 grams, 40.68 grams is carbon. Because we can't use percentage doesn't tell us anything. Percentage is a unitless number. We need units when we're doing. When we're converting grams to moles and moles to grams and back and forth, we need units. It's basically what we're going to try and calculate here is how many moles of each one of these are we dealing with? Because that's what we want. We want the ratio of moles. So yeah, excellent suggestion. Just assume you've got 100 grams, or you could assume you have 1,000 grams or 10,000 grams or 1,000,000 grams. It doesn't really matter. It's just assume you have a certain mass and then convert these percentages to mass also. But since it's percentage, and that means out of 100, why not just make it 100? That way we don't have to do any math. So we can just write down, it has 40.68 grams of carbon. It has 5.12 grams of hydrogen, and it has 54.20 grams of oxygen. So that's what we know. So someone, one of your colleagues or something has done the experiments and actually measured the amount of each one of those in the compound they were given. And typically this would happen, like, let's say someone synthesized a molecule, some organic chemist made something, or they took a known chemical and they added something to it, but they didn't know the effect it had. So you would measure the mass of all the different compounds in there, all the different atoms, different elements, and then figure out what the new formula is. So how are we going to convert grams to molecules? How do we do that?
Molar mass
Molar mass
of carbon and hydrogen and oxygen.
right, because we want to take these grams and convert them to moles. So for each one, I want 1 mole carbon, 1 mole hydrogen, 1 mole oxygen, divided by the mass of 1 mole of each of those atoms. Then I can cross out grams and be left with moles. So what's the mass of 1 mole of carbon?
12.011.
Nope. Grams, right. 12.011 grams. What about hydrogen?
0.008 grams.
And oxygen?
15.999 grams.
So that will eliminate grams and leave us with moles, which is what we want. So how many moles of each one do we have?
The first one would be 3.386895.
3.3869. So 3.387, probably close enough. And hydrogen?
5.07937.
And oxygen?
Yeah. Oxygen is 3.387711.
All right. So we see this.
77.
So we look at these and we can see that we don't have whole numbers here. And we have like 3 1/3, a little more than 1/3 moles of carbon, 3 and a little more than 1/3 moles of oxygen, and a little bit more than 5. So what a lot of students would do here would be, okay, well, let's just round everything. So 3.38 is close to 3. So I'm going to have C3H5O3. But that's not correct, because we shouldn't, when we do this sort of calculation, remember, we shouldn't have to round. We should get precise whole numbers. Now we're not getting precise whole numbers here. So how do we work around that?
Ratio.
What do we do?
Ratio.
Yeah, it's a ratio. Yeah, exactly. We have a ratio of 3.39, 5.08, and 3.39 again. Those are ratios. So what are we going to do with those ratios? How do we get them to whole numbers?
Divide 3.3869 by 5.0794.
That doesn't give us a whole number.
That
gives us a fraction.
Could we add?
How do we add them, though? What are we going to add them to?
Do we need to get add them together and divide it by 3? The average? Oh no.
We don't want an average. We want an exact. We want a precise number.
Excuse me. So you divide them, you get like 0.666. You get like 2/3.
Okay, but we get like 3 fractions. I want whole
Mul-
numbers.
Multiply by 3 for all of them.
Yeah.
Okay. So multiply each one by 3. Why
Yeah.
3?
Because that'll make 3 1/3 go up to 10. And then 5 will go to 15. And the other 3 1/3 will go to 10.
Will it go to 15 though? Because I'm going to have some left over. Let's try that.
Well, it's
Okay.
close enough.
We don't want close to this. Isn't horseshoes or hand grenades. We want to get precise numbers. So if I multiply 5.0794 by, 5.0794 times 3, I get 15.2.
I thought the rule was that you would divide by this.
So
That's not a whole number. That's 15.2.
so
Yeah, someone else had a.
when you divide 3.3869 by 5.0794, you get 0.66689 something. You are close enough to 2/3.
That's still a fraction. I don't want a
2/3.
fraction.
So carbon is two, and H is 3, and oxygen is 2.
So what would be an easier way to avoid us getting fractions to start out with?
3.3869 divided by 3.3878.
Yeah, we divide everything by the smallest number. So that's the way to get around this. Divide everything by the smallest number and see what that gives us. So if we divide 3.3869 by like we'll just use 3.39. So we'll divide that by 3.39, and that'll give us 1. This will give us 1. And what is 5.0794 divided by 3.3869?
1.496.
1.496. Okay, now we're getting somewhere. So 1.496. Now we still have a fraction, but notice 1.496 is really close to 1.5, right? I would say that's close enough to 1.5 that's 1.5. That's only like a few, like 1% or 2 off of 1.5. So now we have 1, 1.5, and 1. So what in whole numbers is our actual ratio?
2/2.
Right. So if we have, once we divide everything by the smallest number, we look and see, a lot of times then, yes, we are going to get a fraction. But, let me erase some of this here. So my ratio is 1, 1.5, and 1. So the simplest way to make that all whole numbers is multiply everything by 2. So 2, 3, and 2. Now, sometimes you're going to see something like 1.333. How do we convert that to a whole number?
Multiply by 3, that gets 4.
Right, multiply that by 3. And if we see like 1.25, how would we get that to a whole number?
By 4?
Multiply that one by 4.
5.
Yeah, so what you'll see is like a lot of times when we do this, you'll get remainders like, 0.333 or 0.666 or something like that, which will multiply by 3 to make it a whole number. If we get 0.25, we'll multiply that by 4. If we get 0.2, we'll multiply that by 5. The key is trying to figure out at the beginning what are we going to divide everything by? Because the first time through, we're going to get some like really weird numbers. So the way to find the simplest ratio between those weird numbers is just to find the smallest number and divide everything by that. So our final answer here would be C2H3O2. That is the simplest ratio of whole numbers that gives us these amounts of carbon, hydrogen, and oxygen by mass. Okay? Does that make sense to everybody? How we do that? We want to convert masses. First of all, we want to take percentages and convert those to masses. Now, masses tell us how many atoms, how many moles of an element there are. And then once we have moles, then we know how they interact with each other. What's the exact ratio of moles? Because that's really what we're dealing with in chemistry, is moles of elements. Shall we do another one?
Sure.
Yes.
All right, which one would you like to do?
The next one.
Okay, yeah, this one, now we have empirical and molecular. So yeah, this is a good way to learn how to do both of them. So, got a compound, and it's this, now this is a hydrocarbon because it only has carbon and hydrogen. So what's the first thing we're going to do?
Smaller mass.
Even before we use the molar mass, what's the first thing to do? Because we have percentages here. We can't use percentages.
There is 100 grams.
Right. Just assume you have 100 grams. You could assume 1,000. You could assume whatever number you want. But you have to have grams to convert to moles. A percent doesn't get us anywhere. So, and if we assume 100 grams, then we don't have to do any math. And we just say, okay, we got 85 grams and we got 14.3 grams. So let's do that. So I have 85.63 grams of carbon for every 100 grams of this compound. And I have 14.34 grams of hydrogen for every 100 grams of this compound. But the question is, how many moles of each one? Because that's really what's happening in chemistry, is moles of elements interact with moles of other elements. So how many moles of carbon do I have?
Times 1 mole.
So that was 12.011 grams, if I remember correctly, right? And you can find this in if you should, by now you should probably have a periodic table. I think at the bookstore they have like laminated periodic tables, or just find one online. I like ptable.com is a good one to use. Or if you just any chemistry textbook you come across will have one. You can even print. There's one in the free textbook you have. You could just print it out from there. But you really should have one handy. So what's my molar mass of hydrogen again?
Hydrogen is
1.008.
8, right.
grams.
7, 9, but let's not be picky. Okay, so this will give us the number of moles of each one. So how many moles of each one do we have?
7.1292.
7.1292 moles of carbon. And how many hydrogen?
That is 14.2559
moles of hydrogen. So now we have two really long, complicated numbers. How are we going to find the simplest ratio between them?
Divide
1
by
over
the
2.
smallest number.
And our smallest number is 7.1292. So we're going to divide both of them by that. 1292. So that gives us 1 carbon. And gee, how many hydrogen? 2. Yeah. So we don't use, so when we write a formula, remember we don't put a 1 after the element. So what we would do is just take out the 1. So it would just be CH2 is the empirical formula. How are we going to figure out what the molecular formula is?
2 times 1.008 plus 12.00 sorry, 12.011 grams. That gives 14 point something.
So what do you actually
and divide?
So rather than describing it, what are you actually doing?
Like calculate the molar mass for the empirical formula first.
Right. You want to figure out, if I had a mole of that, what would it be? You want to figure out, if I had a mole of CH2, if that was the actual molecule, CH2, and we'll learn that that can't be a molecule, but if I had a mole of CH2, how much would a mole of it weigh? What would be the mass of 1 mole of it? So we have 1 carbon, and that's 12.011 grams, and we have 2 hydrogens, so that's 2 times 1.008 grams. So how much would a mole of CH2, what would be the mass of that?
14.027.
14.027
27
grams per mole.
per.
Now we know that the molar mass of the compound, the actual molecular compound, is 42. So the molecular mass is 42.0 grams per mole, and my empirical mass is 14.027 grams per mole. What's the ratio of the molecular mass to the empirical mass?
3.
Yeah, it's about 3. Now, there's going to be some imprecision here because we only have 3 significant digits for 42. So a lot of the times you'll get something like 2.98 or 3.01 or something like that. So if it's that close to a whole number, then it's going to be the whole number. What you have to be wary of is if you get a ratio of something like 3.33. That should tell you that maybe there might be something wrong with one of your calculations, or if you have 3 or like 1 and 2, something like that. If you can change a 3 to a 10 using this is fine. But if you multiply your empirical by something with a fraction in it, make sure that when you do that, all the numbers in your empirical formula turn into whole numbers. Because if they don't turn into whole numbers, then there's something wrong. You should have had whole numbers to begin with. So yeah, so you should have, like, this multiplied by 3 would give you a whole number, but 1 multiplied by that wouldn't. So then you have to go back and make sure you did your calculations properly. But that's how you do this particular example. Find out, you get the empirical formula, figure out what the mass of that empirical formula would be if you had a mole of it. And then there's going to be a ratio between the molecular mass and the empirical mass. And that ratio tells you how much you multiply everything in the empirical formula by. So what's going to be our molecular formula if our ratio is 3?
3H6.
C3H6. Yep. That is either propane. Propane or butane. I'm always mixing them up. I think it's butane.
Propylene. Propane.
Okay. Any questions about how to do that kind of, you're going to be seeing these on tests. So get used to these, knowing what the difference is between the empirical formula and the molecular formula. Anytime you're asked for a molecular formula, you need to know what the mass of 1 mole is, or you'll never be able to figure it out. Another way a question would be is, you might have to figure out what the molecular mass is. So know what the difference is between empirical formula and molecular formula. Molecular is the real thing. All right, what's question would you like to try next?
4.
4. Okay. Okay. Yeah, and there's another one in here that I'll do too that we haven't done yet. But here, bunch of stuff we need to know. Methane, like what the hell's methane? And oxygen react to form CO2 and water. Okay, so anyone know what methane is?
CH4.
Methane is the simplest hydrocarbon. So methane is indeed, whoops, let me go back. Methane is indeed CH4. So CH4 plus oxygen. Now, when I say oxygen, do I mean O? What do I mean?
Oxygen 2.
Why O2?
Because oxygen gas, not
The oxygen of the air.
Right. It's the when I write oxygen, if oxygen is going into a reaction, that means the most stable form of oxygen. This is not the most stable form of oxygen. This is, because oxygen is diatomic, like we talked about a couple classes ago. Pretty much every gas is a diatomic or triatomic molecule, with the exception of the noble gases. The noble gas is pretty much the only gas that is just a single atom. Everything else is generally 1 or 2, 3 or 4 atoms mixed together, connected by sharing electrons. So whenever I say oxygen goes into a reaction, we're talking about the molecule of oxygen, not an atom of oxygen, because it's the most stable form of oxygen. It's the form you're breathing right now, is O2. Because if you had like oxygen, just oxygen, single O, that's extremely dangerous stuff. You don't want to have that around. It's called singlet oxygen, and it's extremely reactive. So methane and oxygen react to give us carbon dioxide and water. So these are our reactants. What are our products?
Carbon dioxide and water.
How do I write them?
CO2 and H2O.
Yeah, CO2 and H2O.
Question.
Yes.
And do you need to write burn on the error?
No.
Okay.
No, you don't have to do that. You could, a lot of times we'll put a triangle there for heat, but yeah, we don't necessarily need to do that here. What's the next thing we have to do?
It needs balance.
We're not
balanced.
We need to balance it. That's right, because we need to have the same number of carbon, hydrogen, and oxygen atoms on both sides. Now, there's a trick to doing these sorts of reactions, and I'll show it to you. Anyone can tell me what kind of reaction this is? We haven't really got
Oxidation.
to this yet.
Combustion.
Yeah, combustion. There you go. Very good. There's 5 points right there. It's a combustion reaction. Why? Because we're burning something in the presence of oxygen. It is an oxidation reaction, but it's extremely rapid, as you know, and that's a combustion reaction, when we burn something very quickly in the presence of oxygen. And generally, when we burn something like a hydrocarbon, especially in the presence of oxygen, we get the oxygen will oxidize the carbon into CO2, and it will oxidize the hydrogen into water. So those are our two products. So when you're balancing combustion reactions, here's the hint to do it, because it's difficult to do a lot of times, because you'll notice you have an even number of oxygen atoms as reactants, but you have an odd number of oxygen atoms as products. And so it becomes tricky to do. So the easiest way to do it is to balance your
Hydrogen.
carbon first. Yes, was there a question?
No.
Okay. So we balance the carbons first. We start with carbons, because generally there's fewer carbons than hydrogens. So we balance the carbons first. So we see there's one over here and there's one over there. So done. Don't need to do anything about carbons. So we don't need to change anything about the CO2. Now let's do hydrogens next. So we've got 4 as reactants. And how many do we have as products?
2.
2, right, there's only 2. So how do we balance them?
Multiply by 2.
How do I do that?
2 waters
Where do I put the 2?
in front of the H.
Right.
Of,
Right, we would put it here. So 2, because we can't change just an atom in a molecule. We're making a whole molecule. So we need to have 2 whole molecules if we're going to do that. So that gives us 4 hydrogens, 1 carbon, 1 carbon. And now we just balance out the oxygen. Always do the oxygens last, because that will make your life easier. So how many oxygens do I have as products?
4.
4, you're right. I got 2 here and I've got 2 there. So now I need to balance oxygens on the left side.
2 oxygen molecules.
Right, so we put the 2 there in front, because I need 2 whole molecules. I can't have 1.5 molecules, although I will show you a trick where we can actually get around that. So now, let's see if everything balances. So we've got 1 carbon on each side. That's good. We've got 4 hydrogens on each side, and we've got 4 oxygens on each side. So everything's balanced. So this, you always have to have a balanced reaction when you're trying to figure out mass of reactants and mass of products. You have to have a balanced reaction, because if you don't have a balanced reaction, those numbers aren't going to add up. You're going to have too many atoms on one side and not enough on the other side. So they have to balance, and then the masses will balance. So the question is, what mass of water, so here, is formed if 9.6 grams of methane, so that's this, 9.6 grams of methane, reacts with 34 grams of oxygen, so 38.4 grams of oxygen, and produces 26.4 grams of CO2. Now, there's 2 ways to answer this question. There's an easy way and there's the hard way. What's the easy way to answer it?
Put the molar mass under the mass.
No, easier way than that.
You add
Easier
the-
than that?
Go ahead.
Add and subtract.
Right.
Somebody had it there.
Add the reactants together and subtract the product of the CO2,
Exactly.
and you will have the other.
Exactly, because the mass of the products, the mass of the reactants has to equal the mass of the products. So in that situation, we don't even need to have a balanced equation, because we know that whatever the reaction is, when it goes to completion, whatever the mass of the reactants were has to be the mass of the products, because we can't destroy or create mass. It just changes place. It just changes shape. It goes into a different form. So if we just add 9.6 plus 38.4, what's the mass of the reactants?
That is 48.0.
So our total mass of reactants is 48.0. That tells us that the total mass of the products has to be 48.0 also. It has to be exactly the same. So if 26.4 grams of my product is CO2, the rest has to be water. So what's the mass of water?
21.6.
21.6. So, like I said, that's the easy way to do it. Now let's do it the hard way. So,
Put the mass there.
so to do it the harder way, we actually need to calculate moles, just to be absolutely sure. And hopefully we should get 21.6 out of this.
Can we do the easy way on a test or no?
Oh, definitely.
Okay, cool.
Good question.
Definitely do that. If like for instance here, if it didn't say how much carbon dioxide, if it just said 9.6 grams of methane, actually all I could say, all the information you would need is 9.6 grams of methane. That's it. That's the only bit of information you need to figure out the rest of this. Actually, let's do that. This is the only bit of information you need to solve this problem. Is the mass of methane. You don't need anything else if you have a balanced equation. Yes.
Do we need the state of the matter after the
if you're told to show state of matter, then yes. So in this sense, so we would have gas. CH4 would be a gas. O2 would be a gas. CO2 would be a gas, and H2O would be a liquid.
Would that be water vapor?
No, usually you say whatever the state of matter would be at standard temperature and pressure. So 1 atmosphere, 25 degrees Celsius. So at that temperature, water is a liquid. That'll become important when we do thermodynamics, because it takes energy to move matter from one state to another. So, right, but yeah, we're not doing that right now. So, yeah, so that was the easy way. We got 21.6. Let's do it the hard way. So the only information I'm going to use is the mass of methane. So I have 9.6 grams of CH4. So we need to figure out how many moles of CH4 is that. So how do I determine that? I want to convert this to moles.
Put the molar mass. Yeah.
What's the molar mass of CH4? You can look it up. I don't care. You don't need to calculate it every time.
So it is 16.043, which is 16.0 is enough.
So how many moles is that?
That is 16.043. That is 0.598 39, etc.
All right, so we have that many moles of CH4. So if you have that many moles of CH4, how many moles of water are we going to make?
Can I ask a quick question?
Yes, of course.
Especially in like going over the labs and whatnot, because a lot of these numbers, they have like very excessive digits. And I know that you said
excessive digits.
Yeah. I mean, and I know that you were saying like we're trying to use as many as possible to be accurate, but I did see that you rounded a couple of them. It's like, is there like I
round at the end. I don't round. I round till I get to the very end. Right now, yeah. I mean, I just round it because this is going to be close enough to get us to our answer.
Okay, yeah. So
Yeah.
my question is, I want to make sure I'm doing it your way. What is your opinion of it being close enough? Like how many
Like
digits are too many?
4 or 5 digits is plenty.
Okay,
Yeah,
cool.
because
Thank you.
usually I go by how many digits am I given. So here I'm only given 2. So if I
Right.
figure if I'm using 4, that's because I'm going to have to round it back anyway. So,
Okay.
but using more than like 5 or 6 is just kind of superfluous, really. But just like 4 is probably enough. If you want to write down 5, that's plenty. But there's really no point in writing 6 or 7 or 8 digits.
Okay.
Because yeah.
All right. Thank
Sort of
you.
the rule is basically like 1 or 2 more than you need.
Oh, okay.
Yeah.
Thanks.
Yeah, no worries. So while I have you on the line, if I have this many moles of methane, how many moles of water am I going to get?
1.196.
Where's that number come from?
That is 2 times 0.598.
Where did you get the 2 from?
Two molecules of not 2 molecules of water. The
Right.
two
So
in front.
there is 2 molecules of water for every 1 molecule of methane. And so we need to have the balanced reaction to see what the molar ratio of methane to water. So we would take this number and multiply it by 2 moles water over 1 mole CH4. That cancels out moles of CH4 and leaves us with moles of water. That's why I always multiply and don't divide, because I like to be able to cancel my units out. So here I'm canceling out grams and I'm left with moles of methane. Then I'm canceling out moles of methane and I'm left with moles of water, because that's the number that's what I'm looking for. And then next I want to change out grams, because the question is what mass of water is formed, not how many moles. It's mass of water. So now I finally want mass of water over moles. So what's the mass of 1 mole of water?
18. Something close to 18. Let me see.
Yeah, it's gonna be pretty close to 18. Anyone have the number? I think it's like 18.02 or something like that, or 04. I can't remember.
18.02.
02. There we go. So to get my answer of moles, then back to grams, I multiply this number by this number and by this number. And that gives me grams of oxygen, or grams of water. So how many grams of water do we finally wind up with?
21.56.
21.56 grams. When we round it, of course, here there's only 2 significant digits, so our actual answer would be 22. So we would need to round this to 2 significant digits. But you can see it's the same answer we got before. So the answer we got before was 21.6, and we get the same answer this way. So that tells us we must have done it correctly.
Excuse me.
Excuse me?
So would it be easier to do like this? Let me over what is that? 1.6. Sorry, 16.043, and here is what? Here is x. X over.
Yeah, you can do it that way if you want. I'm just showing. I mean, I like to keep track of my units. So if you want to do it a different way, you're free to do that. Okay.
Because the ratio would be the same.
Yeah, you can do it that way if you want. I like to see the units in front of me, so that I know I'm doing it properly. All right, so that's how to do that particular problem. I think next one might have been another. There we go. Yeah, I want to do this one because this is another example of a question you're going to get on tests all the time. And this is how we actually measure masses of carbon and hydrogen in a compound. We actually burn it and then see how much CO2 and how much water is made, and then figure out what the mass of the carbon and the hydrogen is. This is actually how you do it. So it's a combustion reaction. So we don't know what the compound is. And so a combustion reaction would mean, let me get a nice color here. So it means something X, we don't know what it is, plus oxygen gives us CO2 and H2O. So what we're going to do is figure out how much carbon and how much hydrogen from the masses of CO2 and H2O. So it tells us we've got 4.554 grams of CO2 and 2.322 grams of H2O. So how can I, using this information, how am I going to figure out how many moles of just carbon are in this particular sample?
First use the molar, the percentage of mass of the carbon and carbon dioxide.
Didn't we find the mole of carbon?
The molar mass of carbon dioxide.
Okay. Anyway, what I heard? Like, what did you say there?
The molar mass of the carbon dioxide.
What are we going to do with that?
To calculate the moles of the carbon dioxide, which is the same as the moles of carbon.
Yeah, that's the key to the whole thing, is however many moles of CO2 we have, that's the same amount of moles of carbon, because there's 1 mole of carbon in every mole of CO2. So if we figure out how many moles of CO2 we have, that also answers how many moles of carbon we have. So I'm going to take this and multiply it by 1 mole over the molar mass of CO2, which is like 44 point something. Someone wants to look it up for me.
That is 44.01.
And then water again, what was that? It's 18.02, I believe.
Yeah.
Last time we checked. So how many moles of CO2 do we have? So how many moles?
That is 0.103476.
1037.
3476.
So that's the number of moles of CO2. It's also the number of moles of carbon.
C.
So when we're dealing with water, now we have to remember there are 2 moles of hydrogen atoms for every mole of water. So here we're dealing not with hydrogen molecules, but hydrogen atoms, because in a molecule of X, whatever X is, has atoms of hydrogen in it, not molecules of hydrogen in it. It's actual atoms, and each one with a particular mass. So for every mole of water, there's going to be 2 moles of hydrogen atoms. So how many moles of water do we have?
322 over 18.2. That is 0.12886.
So how many moles of hydrogen do we have?
2 times that.
Mm-hmm.
That is 0.2578.
So this is what we've been looking for the whole time. Remember, when we're looking for an empirical formula of a compound, what we want is the ratio of carbon and hydrogen. And now we have it. But what we actually need, remember, is a whole number. So we've got our mass, we have our moles of carbon, and we have our moles of hydrogen. So remember, how do we convert this to whole numbers?
Divide 0.1035 by the 2 things, the 2 numbers.
So that gives us 1. And what's my ratio of, what's my answer for hydrogen?
2.49, which is 2.5.
Right. So again, if you get something that says 2.5, if you get a 0.5 in there, the easiest way to change that to a whole number is just multiply them by 2. If you get 0.33, multiply that by 3. If you get 0.2, multiply that by 5. So in this instance, we have like 2.5 and 1. So just multiply both of them by 2. And that gives us C2, and that gives us H5. So our empirical formula for the compound is C2H5. Now, how would we figure out what the molecular formula of the compound?
Can I ask another question real quick?
Mm-hmm.
Okay, so just right now, when you were multiplying times 2, and you said like, oh, it depends on what number. Can you go over that again?
Oh, it depends on which number. I'm sorry, I didn't understand.
Yeah, me either.
That's why you're asking the question. You're wondering where we came up with this?
No, when you're multiplying it by 2, how come? Like, how?
Oh, yes. Okay. Yeah, because if we don't multiply by 2, we would get this as an empirical formula. We would get CH2.5. And that doesn't make any sense. We can't have 2.5 atoms of hydrogen. We can't have that. They have to, atoms, you can't split them apart. They have to be whole numbers of them. Right. So if my ratio is 1 to 2.5, and I need to convert them to whole numbers, well, the easiest way to do that is just multiply both of these things by 2. Now I have C2 and H5. Those are whole numbers. That I can use. And it's the same ratio, because the ratio of 2.5 to 1 is exactly the same as the ratio of 5 to 2. And its ratios is what we're dealing with here. Okay. We're getting how many moles of one and how many moles of the other, and what's the ratio between. That's all we're dealing with. And that's the same ratio as 0.1035 to 0.2578. It all depends how much material are we actually going to burn. If we burned a ton of it, we might be able to get 5 to 2 or 2.5 to 1. But if you burn a small amount, you're going to get these really weird numbers, very small numbers. We need to figure out what the ratio is between these small numbers. So you divide by the smallest number, and that usually gets you on the road to having whole integer numbers.
Okay. And then you round those numbers on the left, right? Because
the only time you really round, we don't really want to round them. If we get something like a ratio of 2.49, that's really close to 2.5. That's not much of a rounding. What I would worry about is I would worry if I had a number like 2.4, because then I'm looking at 2.4. It's like, ugh. If I multiply that by 5, I'll get a whole number. But is it 2.33 and I need to multiply by 3? Or is it closer to 2.5 and I only multiply by 2? It's like, ugh. So if I had like something like 2.4, I would probably go back and redo my calculations, because I really want to make sure that you don't want to round this number too quickly.
Okay.
Yeah, because like I said, if you have like 1.3, that's probably 1.33333, and you just multiply that by 3. You don't want to take 1.3 and round it back to 1.
To 1. Okay.
Yeah, don't do that.
All right. Thanks.
Yeah, no problem. But yeah, we're going to have a lot of these sort of questions. And sometimes there's going to be oxygen in the compound. And when we do that sort of question, we're going to have to figure out how much carbon, how much hydrogen, and the oxygen we're not going to be able to calculate directly, because when we burn that compound, it's going to be in the presence of oxygen. In fact, it's going to be in the presence of a high concentration of oxygen. So the oxygen that's in the compound, very little of that will actually be turned into water and CO2. So we'll have to figure out how much carbon, how much hydrogen, and then the rest of the mass of the molecule will be oxygen. So we'll have to calculate that indirectly. But I'll show you how to do that when we get to it. Okay. Let's do, we got plenty of time. Let's do a couple more. What's the next one you'd like to try?
Professor?
See.
I'm actually a little confused still. Sorry, I know you
No
erased this.
problem. No, that's the whole point of this, is to learn how to do these things. On this one in particular, or a previous question?
This one.
Mm-hmm.
So I'm still a little confused on how we got 0.1035 moles. I know we took the grams of CO2 and H2O and we multiplied it by a mole and we were left with grams, but I don't know what we did to get.
Okay. So, can I go back? Where's my undo button? Oh, there we go. Yeah, so we got to this number. So let me erase some of this because there's a whole lot going on here. All right, so we got to these two numbers. The moles of carbon came from the number of moles of CO2. Because in our reaction, when we combust something, we basically when we burn something in the combustion chamber, and when you burn something in a combustion chamber, you have an extremely high pressure of oxygen, so it burns really, really fast. And so we get CO2 and water as our products. And so we get that amount of CO2, and we get this amount of water. And that's all we have to go on. So what we need to figure out is how many moles of carbon did we get as products? How many moles of hydrogen do we get as products? Because that is the number of moles of carbon and hydrogen in the original compound. Because all of the carbon, the only source of carbon is from our compound X, whatever it is. All of the carbon that's in the CO2 came from compound X. All of the hydrogen that shows up in the water also came from compound X. So if we figure out how many moles of carbon are in the products and how many moles of hydrogen are in the products, we have figured out how many moles of carbon and hydrogen were actually in the reactants. And our reactant, the only place that those could have come from is from compound X. So to figure out the number of moles of carbon, we just figured out how many moles of CO2 that is. And because there is 1 mole of carbon in every mole of CO2, right? If I have a mole of CO2, I automatically have a mole of carbon as well. Would you agree with that?
Yes.
Yeah. And so if I have a mole of water, how many moles of hydrogen atoms do I have?
1.
Two.
Oh,
There's
2.
2 atoms of hydrogen in every mole of oxygen. So if I have a mole of oxygen, I have 2 moles of hydrogen atoms. And it's atoms I'm interested in because my compound X is made of atoms. It's not made of molecules, it's made of atoms, right? It is a molecule that's made of atoms. So I need to know how many atoms of hydrogen there is. So we figured out that there was 0.01035 moles of carbon, because that's the same number of moles of carbon dioxide there were. Now, hydrogen was a little trickier. There was half that many moles of water. There's around, well, half that, around like 0.112 moles of water. But since there's 2 moles of hydrogen atoms for every 1 mole of water, we figure there's twice as many hydrogen atoms. And so that's how many moles of hydrogen atoms there are. And then we just did the same trick we used last time. This is to figure out the empirical formula. We just divide by the smallest number of moles. And that'll give us a quick a shortcut to getting a whole number. So if we divide both by the smallest number of moles, 0. The reason for doing that, because this immediately gives us 1 for like the smallest number. That immediately becomes 1. So I've got 1 carbon. This becomes 1. And the other, when we did the math, was 2.49, which is really close to 2.5. Close enough that we don't feel too bad rounding it. So then I've got 1 mole of carbon and I've got 2.5 moles of hydrogen. But I can't have 2.5 atoms of hydrogen in a compound. So what would you do if you had that?
You would need to multiply it by 2.
Exactly, because that's the same ratio. Because remember, in none of these calculations do we ever have exactly how many moles of one thing and another thing are going to be in the compound. All we have is a ratio. That's all we have, because we don't know what the molecular formula is. We don't know what it is. All we can figure out is what's the ratio. That's it. That's the only thing we can figure out. And so the simplest ratio that has whole numbers is 2 and 5. That's as simple as we can make it without saying, hey, shh. That's the simplest ratio we can make without getting fractions, is 2 and 5. So we write it down finally as C2H5, okay?
Okay, thank you so much, Professor.
Hey, no worries, no worries. Yeah, anybody, I mean, I'm glad you said that, because, you know, there's going to be like 20 other people in class who I wish I had asked that, because that's the whole thing. I mean, I always find that, yeah, pretty much half the class is not willing to ask the question, and then they get really frustrated, and then they go like, oh, thank God she asked. Oh, yay, now I can get it too. So yeah, never feel bad about asking a question. That's the whole point of this exercise. All right, so we have time for a couple more. What would get? This is a long one. It's like 5 pages or something. So what one would what one is making people scratch their heads?
Sorry to be repetitive, but can you do number 6 just so I can get it?
We haven't done 6 before. Why would that be repetitive?
Oh, okay, I thought it was the same.
Let's have a look.
Process.
Is that another combustion? Oh, that is another. Oh, yes, right here. Yeah, this is perfect. So I'm going to have you guys lead the way on this one, because this is just what I talked about. Because now I don't have compound X anymore. Now I have compound Y.
Excuse me.
Yes.
When you determine the mass of carbon of something, can you use concentrated sulfuric acid?
You're wondering how we capture the carbon? I can't remember. I know we capture the water with sodium hydroxide. I can't remember what's used to capture the carbon. It might be something like that.
I mean, capture the water. Use the sulfuric acid, but you left but what's left is all carbons, right?
Yeah, you capture the CO2. I can't remember what we used to capture the CO2. But yeah, we don't convert it to carbon. We just capture the CO2. Because it's not graphite we're capturing, it's CO2. Yeah, so I think it's a base.
I mean, I'm not saying this one. I'm saying you're determining the the mass of carbon in a compound. Can you use concentrated sulfuric acid to remove the H2O in the hydrogen carbonate and
and just leave? I think it's actually easier to do it this way, because that's kind of a messy process.
Okay.
Yeah, you mean turning it to pure carbon?
Yeah.
Yeah, you could, but I don't think it's nearly as accurate.
Okay.
Yeah, because it's difficult to get all that, and you don't know whether you would never know whether your reaction went to completion either. So that's not an easy way to do it. So here we've got compound Y. Now compound Y has CH and oxygen in it. And now remember what I told you, the problem with there being, now we have two sources of oxygen, and that's an issue, because the oxygen that goes into the carbon dioxide and the water, we don't know where it came from. Now, when we burn this, it's going to be in a very concentrated, high pressure atmosphere of oxygen. So most likely, almost all of the oxygen in the CO2 and the water are going to be from the atmosphere, and hardly any of it is going to be from compound Y. But we can't take that for granted. So the way we're going to figure it out is determine how much carbon we have, how much hydrogen we have, and then the remainder must be oxygen. So that's how we're going to do this, okay? So what do we do first? So let's put down the information we have. So we have 2.400 grams of compound Y, and we isolate 4.171 grams of CO2 and 2.268 grams of water. So what I want you to do is figure out how many moles of carbon and how many moles of hydrogen atoms do we have. So go ahead and do that.
Do that now?
Yeah.
Or
now remember how we did it last time, and do the same thing. So we need to figure out moles. We need moles of carbon. And here we need moles of hydrogen atoms. How do you do that? First of all, how do you do that? How do you get to, before you do the math, how do you get to moles of carbon?
The moles of carbon hydroxide is the moles of carbon.
Carbon dioxide, not hydroxide, yes.
Yeah, dioxide.
So the moles of carbon dioxide will be equal to the moles of carbon, because there's a 1-to-1 ratio of carbon to carbon dioxide because there's only one carbon in it. Now with water, how do we get from mass of water to moles of hydrogen atoms?
The moles of water times 2 is the moles of hydrogen.
Right. So who's got moles of carbon and moles of hydrogen? All right, so anybody got moles of carbon for me?
Is it 0.0948?
So 0.0948.
Yes.
Okay. Moles.
That's what we got, but I'm
What
not
about
really sure.
what about hydrogen?
I think there's an easy way to do it.
Would it be okay if we went directly to converting it to grams right after that?
Yes.
Okay.
But you're going to use this. You're going to use this information because that is, in fact, how many moles of carbon there are in compound Y. But you're right. We're going to need to convert that to grams too. That's a little different. When there's oxygen present, yeah, we have to follow slightly different procedure. So how many moles of hydrogen do we have? How many moles of hydrogen, Jerome? Can you tell me? Yeah, my dog is useless at these calculations. Yeah, you're more of a biologist, aren't you? Yeah. So how many moles of hydrogen? Someone's got to have it. Nobody? Oops. Oh. How many moles of hydrogen atoms? If I keep asking, someone will tell me.
Yes, 0.252.
0.282?
52.
0.252. Okay. So mark this because that is actually how many moles of carbon and hydrogen in compound Y. But how are we going to figure out how many moles of oxygen are in compound Y?
Well, since you have the grams of carbon and hydrogen, you can
No, but we don't yet. How many? We need to figure out how many. You're right. We need to figure out how many grams of carbon and hydrogen we have. So how do we do that? Because right now we've got moles. We need to get grams.
Calculate the mass of oxygen gas first.
No.
No.
Nope.
Convert
we have no idea how much oxygen was used. We just used
we used
an excess of oxygen gas.
Excess?
Yes. We have no idea how much was consumed.
Use the molar mass.
Molar mass of
carbon and hydrogen.
There you go. Yeah, we have moles of carbon and hydrogen. Let's convert that to grams of carbon and hydrogen. Exactly right. So we multiply this by 12.011 grams per mole. And we multiply this by 1.008 grams per mole. Now that'll give us grams of carbon and grams of hydrogen. So how many grams of carbon do we have? So grams of carbon should be a quick multiplication there. What do you think, Jerome? Can you multiply?
One 1.14.
1.14. I think we want at least 4 significant digits.
So it's 1.13864.
1.13864. Close enough. There we go. So that's how many grams of carbon. What about hydrogen? How many grams of hydrogen do we have?
.2537.
0.2537 grams. Remember, grams. Now, so whatever's left over has to be oxygen. So if we start it with 2.4 grams of compound Y and 1.138 grams of it is carbon and 0.254 grams of it is hydrogen, the rest is oxygen. So how many grams of oxygen do I have? Can you get down? There you go.
1.008
grams of oxygen. Okay. So we have 2 of the 3 pieces of information we need to answer this question. We have moles of carbon here. We have moles of hydrogen here. We don't have moles of oxygen. And we can't just subtract because we have a mass of compound Y. We have no idea how many moles there are. We just have some amount. So we need to figure out moles of oxygen as well. So how are we going to do that?
Devoid that one. Connection.
So how are we going to get moles of oxygen? I have
molar mass.
I have 1.008 grams of oxygen. What am I going to do with the molar mass of what?
Oxygen. So you just multiply it by 1 mole over 15.99 grams.
There you go.
Of oxygen.
And that's going to give us moles of oxygen. And how many moles of oxygen is there?
0.063 moles.
That it?
Well, 6302.
Okay, 630. Okay, close. Yeah, there we go. Moles O2. So now we got all the information we need. We have moles of oxygen, we have moles of hydrogen, and we have moles of carbon. So we're good to go. So how am I going to get my empirical formula?
divide all the numbers by 0.0630.
That is the smallest number. The moles of oxygen is the smallest number. And it usually is. It's either oxygen or carbon, usually oxygen.
Excuse me?
Yes.
How did we get 1.008 grams of oxygen again?
Oh, because we figured out we have, let me write it down for you. So we figured out that's how many moles of carbon we have. So then we figured out, well, if that's how many moles of carbon we have, we must have this mass of carbon. And then we figured out how many moles of hydrogen we had from the amount of water. And if we know how many moles of hydrogen we have, then we know the mass of hydrogen too. And once you have the mass of the hydrogen and the mass of the carbon, well, the only thing left in compound Y is the mass of the oxygen. And so we just took the total mass of compound Y is 2.400 grams, and we just subtracted the mass of hydrogen and subtracted the mass of carbon. And all that was left was 1.008 grams.
Okay,
because there's only three things in compound Y.
Oh, so the oxygen of 1.008 doesn't include the O2, but just the one.
No.
Why?
Because the problem here is that there's two sources of oxygen. There's oxygen in compound Y, and there's the oxygen we're burning with. So we'll never know exactly how much of the oxygen in our products came from either one. There's no way to know. So the only way to get around that is to figure out how much carbon and hydrogen precisely, and whatever's left had to be oxygen.
Excuse me.
Yes.
Can we use the product mass, total mass of product minus the 2.400 gases?
No, because we don't know what the mass of O2 was.
Get the mass of the oxygen gas.
We don't know what the mass of oxygen gas is.
I mean, 4.171 plus 2.268 minus 2.400.
That doesn't give us any additional information. That only tells us how much O2 was used. That doesn't tell us how much oxygen is in compound Y.
Then use the total oxygen and the product minus the oxygen gas. That gives. Is that?
No, you still can't do that because you don't know. No, I don't think that would work either. You could try it that way and see if you get the same
Calculate
answer.
the percentage. Okay.
You could try it that way. See if that works. I know that this way definitely does work. Okay. So now we have moles of oxygen, moles of carbon, and moles of hydrogen. So we're going to divide by the smallest number, and the smallest number is oxygen. So that gives us O1. How many moles of carbon do we have? So it's 0.9. What is it? Is it 1.5?
Yeah.
And what about hydrogen? So it'd be 2.52 divided by 0.0630.
That would be approximately 4. 3.999.
3.999. So that's 4. Yeah. So H4. So we have 1 mole of oxygen, 1.5 moles of carbon, and 4 moles of hydrogen. And so we can't have a half. So what do we do?
Multiply by 2.
Yeah. Multiply everything by 2.
C3, H8, O2.
Oh, wait a minute. Right, so that would give us C3H8O2. You normally put the carbon first, the hydrogen second, and the oxygen last. Not always. That's usually how we would write them. You could write them in any order. You won't be wrong. But in general, chemists put the carbon first, the hydrogen second, and the oxygen last. So C3H8O2. So did that make sense to people? That was an awful lot. There's an awful lot of calculations in that question. Hey, shh. Shh.
Thank you.
All right, so we can do one more before we go, though these dogs obviously need to go outside. So is there one in the second section you'd like to have a look at? Or really any of them, that's fine with me.
I just have a quick question about like number 3, number 4.
Going back? Like this
no,
one?
on part 2.
Part 2, okay.
Yeah. Do you want us to calculate the molar mass, or can we look it up?
Which one are we looking at?
Right.
Which question?
Number 3 and 4. Not the multiple
I don't know if I
choice
have
one.
these.
Or how many moles of N2O4?
Oh, okay.
I guess yours is a different order.
This one.
That one?
Yeah.
You want us to calculate the molar mass?
Oh man, that's an easy one. Yeah, just you can look up the molar mass. That's fine.
Okay.
Yeah, if I don't say, calculate the molar mass, then yeah, don't bother. Just look it up.
All right, thank you.
Yeah, yeah. I mean, that's what I do when I write out the keys for these things. Will, you too, stop. God damn. Anyway, any other questions before we go? Yeah, the rest of them are a lot more straightforward. But we haven't had those combustion questions before, and get used to them. There's going to be a lot of them. So just to hint, hint, hint. All right, the rest of it looks kind of clear. Or everyone's just too too beat down. I get it.
You
All
said
right.
some of
go
the
ahead.
Recitation questions are going to be similar to that on the test.
Very similar. Yeah, I mean, they're not going to be exactly the same because then you can just look them up. But they'll be, yeah. When I say that, get ready for combustion questions, you can pretty much guarantee there's going to be combustion questions on the test. I mean, there's going to be a combustion question there.
Okay.
So if you know how to do combustion, you're good to go. So actually, yeah, before I go, why don't I show you the trick for balancing combustion reactions? Because some of them are different. Hey, can you bite me? Okay, this should show you the trick. Man, I know you want to go outside. Just give me a second here. My girl just wants to be petted. Okay. This is a good rule of thumb for doing combustion balancing. So let's say I have like a more complex carbon molecule. Let's say I have C11H24. Let's say I'm burning that. So it's a long chain, like kerosene or something like that. So I'm burning that. I'm in the presence of oxygen, and I'm making our good old friends CO2 and H2O. So, like I said, what you want to do in these situations is balance your carbon first. So first we do carbon, and second we do hydrogen. And you save oxygen for last because the oxygen goes into both products, so it makes it a little tricky to do. So carbon, pretty straightforward. So how many moles of CO2 are we going to have? So based on this formula, how many moles of CO2 am I going to create?
11.
11, right, because I got 11 carbons here, so I need 11 carbons over here. So 11, right. So how many waters am I going to need to balance my hydrogens?
12.
12, yep. So far so good. Now, oh, damn, I should have picked a harder one. So now, oxygens, let me start over, because yeah, this is going to be too easy. Let's say it was C10. There we go. I think it's easier when it's an odd number. Yeah, let's do C10. Yep. All right, let's try that again. Okay. So, outsmarted myself. So I've got C10H22. All right, let's do, hopefully this one, yeah, I think this one will be a little harder. Okay.
Don't you want the hydrogen to have an odd number?
No, I mean, if I have C10, that's how many hydrogens I'm going to have. Yeah, if there's no double bonds, if we say it's fully saturated, if there's no double bonds, that's how many hydrogens we're going to have. So your hydrogens are basically determined by how many carbons you have.
What I mean for the problem.
Yeah, but I don't want to make up a compound that doesn't exist. Then we might not be able to balance it. So this is how many we're going to have. All right, let's try it. Let's try it again. Okay, so I think I outsmarted myself the first time. So how many CO2s this time?
10.
10. All right, that wasn't so hard. How many waters?
11.
11. Yeah. So, so we have the same. You always have the same number of CO2s as you have carbons. That one's pretty straightforward. And then hydrogens, you have half as many waters. That's fine. So we've balanced our carbon. We've balanced our hydrogen. Now we have to balance our oxygen. So here I've got 20, right? And here I've got 11. So I've got a total of 31 oxygens as products. How many oxygen molecules would I need for that many oxygen atoms?
15 and a half.
15 and a half. Or 31 divided by 2. Now, I can't have that in I can't really have that in a balanced equation. When we start doing thermodynamics, we can have numbers like that, but we can't have numbers like that in a balanced equation, because I can't have like half atoms or half of a molecule. There's no such thing as half of a molecule. There's half of a mole, yes, but there's not half of a molecule. So what am I going to do to get whole numbers all the way across?
Double everything.
Exactly. Multiply everything by 2. So then I will put a 2 there. This becomes, whoops, let me go back. This becomes 31. That becomes 20, and that becomes 22. Yeah, so now I have 31, 20, and 22. So that's how you do those more complicated combustion reactions. Carbons first, oxygens, or hydrogen second. Oxygens always last. And if you have to do something weird, if you have to double everything, that's fine. Go ahead and double everything. Because it gets tricky when you have an odd number of oxygen atoms on one side and an even number on the other. And you're always going to have an even number of oxygen atoms as reactants because they come in pairs. There's no way to avoid that. So that's the trick to doing combustion balancing reactions. Sometimes like you've seen, it's easy when there's an even number of odd number of carbon molecules, difficult when it's an even number.